No matter what your business is, whether it's hauling materials on high-speed interstates, navigating on busy city expressways, or transporting the most valuable cargo of all, people, on crowded city streets, it is your equipment that you rely on to get the job done effectively and safely. It's hard to imagine a more vital part of safe, reliable operation than the air brake systems, and that's what this presentation is all about. A typical air brake system can be divided into several distinct parts: the supply system, the front and rear service systems, and finally, the trailer. This presentation is the first of a four-part series and deals with the operation and maintenance of the air supply system. During the program, we'll point out areas of maintenance concern. Although brake systems and components may vary from vehicle to vehicle, the air supply system, shown here in gray, is basic to all. The major components are the air compressor, supply, front axle, and rear axle service reservoirs, governor, and air dryer. The primary component of the supply circuit is an air compressor, such as this Bendix 2-flow 550. Powered by the vehicle's engine, the air compressor converts atmospheric air into compressed air, energy needed to power the vehicle's brakes. The compressor components we focus on during this presentation are the crankshaft, connecting rods, rear end cover, rear main bearing journal, pistons, cylinder bore, inlet valve, discharge valve, and discharge port. The compressor crankshaft and connecting rods convert the rotational force of the engine to a vertical linear force in the compressor pistons. The compressor is lubricated by pressurized engine oil, which in this case enters the rear end cover, flows to the rear main bearing journal, and through a passage in the crankshaft to the connecting rod bearings. Oil that escapes from around the bearings falls to the bottom of the crankcase and is returned to the engine. This oil return is important because it prevents crankcase flooding, which results in compressor oil passing. Let's take a look at the air compressor from a front view, revealing a single piston only. During the intake stroke, a slight vacuum is created above the piston in the cylinder bore, causing the inlet valve to open and move from its seat. Filtered atmospheric air flows into the bore until the piston reaches bottom dead center and begins to reverse its travel. As the piston begins its compression stroke, the inlet valve closes, and the air in the cylinder bore is compressed as the piston approaches top dead center. During air compression, the discharge valve opens, allowing compressed air to flow from the cylinder bore past the open valve and out the discharge port into the supply reservoir. Returning to our full cutaway view of the compressor, we find that since the compressor contains two cylinders and the crankshaft has 180-degree opposed journals, one piston will be on its intake stroke while the other is compressing, building to maximum pressure. While this is occurring, a constant flow of engine coolant is routed through the cylinder head cavities to dissipate the heat generated by the compressor during air compression. Rapid buildup of air pressure depends upon proper opening, closing, and sealing of both the inlet and discharge valving and unobstructed flow of air in the cylinder bores. Check for any restrictions to the flow of atmospheric air into the cylinder bore or the compressor discharge line leading to the supply reservoir. The obstruction of atmospheric airflow into the cylinder bore will cause the vacuum above the piston to draw oil past the piston rings, resulting in oil passing. An obstruction in the compressor discharge line leading to the supply reservoir will cause the compressor to run hot, build carbon deposits, and pass oil despite adequate coolant flow. Next, let's look at the Bendix D2 governor and how it interacts with the compressor and supply reservoir and later the air dryer. The governor is used to control the compressor and thereby regulate air pressure in the supply reservoir. The governor's main components are the reservoir port, piston, inlet exhaust valve, pressure setting spring, and governor unloading port. An air line connects the governor to the supply reservoir. Reservoir air enters the governor at its reservoir port. As air from the compressor builds reservoir pressure, the governor's piston and valve move together against the resistance of the pressure setting spring. When reservoir pressure reaches the cutout setting of the governor, typically 120 psi, the piston will have moved sufficiently to seal the exhaust and open the inlet. Reservoir pressure flows past the inlet, through a passage in the piston, and out the governor unloader port to the compressor unloader mechanism. Air from the governor enters the compressor and acts upon the unloader pistons, which move and hold the compressor inlet valves off their seats. With the compressor unloaders pressurized, air enters and leaves the cylinder bores through the open inlets, and air compression ceases. Because the pistons are 180 degrees opposed, air is shuttled from one cylinder to the other as the pistons move up and down. When supply reservoir pressure drops to the cut-in pressure of the governor, typically 100 psi, the governor pressure setting spring moves the piston, closing the inlet and opening the exhaust. Air in the compressor unloader mechanism flows back to the governor and is exhausted. With air pressure removed, springs move the unloader pistons, allowing the inlet valves to return to their seats, and the compression of air resumes. Here's a service tip. Make sure the air line between the supply reservoir and governor is unrestricted. Otherwise, the governor's function will be impaired. If either the governor or compressor unloader mechanism fail to function, the compressor would continue to compress air. To protect the air systems against a failure of either the governor or compressor unloader mechanism, a safety valve like the Bendix ST3 is installed on the supply reservoir or air dryer if the vehicle is so equipped. Generally set to open at 150 psi, the safety valve employs a spring-loaded stem resting on a seated ball valve. When reservoir pressure exceeds the valve setting of 150 psi, the ball moves off its seat and air is exhausted through the exhaust port. The safety valve should be checked periodically by pulling the exposed stem. Air should escape when the stem is pulled and cease when released. A dual circuit brake system generally consists of a minimum of 3 reservoirs: the supply reservoir, the front axle service reservoir, and the rear axle service reservoir. The service reservoirs supply both the front and rear axle brake circuits. Air from the supply reservoir flows through single check valves to fill, protect, and separate the service reservoirs from each other. The Bendix SC1 single check valve allows air to flow in one direction only. The Bendix SC1 consists of a supply inlet port, inlet valve, spring, valve seat, and delivery port. Supply reservoir air pressure overcomes a light spring force to move the valve off its seat, allowing air to pass through the valve into the service reservoir. If the supply reservoir air pressure is lowered for any reason, the check valve closes and prevents service reservoir air from flowing back into the supply reservoir. As required by federal regulation, braking pressure for each service reservoir is registered on a dash-mounted air pressure gauge or gauges. A low-pressure indicator switch, such as the Bendix LP3, is installed on both service reservoirs. Also required by regulation, the LP3 activates a visual warning, generally a dash-mounted warning light and a buzzer. When reservoir pressure falls below a safe minimum, typically 60 psi, electrical contacts in the low-pressure indicator switch close. They remain closed until reservoir pressure rises approximately 15 psi above its safe minimum setting. In addition to providing a place to store air, the reservoirs also serve as a collection point for contaminants produced during air compression, such as water from the air and oil from the compressor. Oil, water, and vapor are contained in the hot pressurized air from the compressor. When cooled in the air lines and reservoirs, these contaminants condense and collect in the bottom of the reservoirs. Removal of these harmful contaminants is essential to ensuring proper valve operation. This is most easily accomplished using a simple drain cock, which when opened permits air pressure, along with contaminants in the bottom of the reservoir, to be expelled. The check valves and low-pressure indicator can be tested by observing the reaction of the dash gauges and low-pressure warning device as air is drained from individual reservoirs using the drain cocks. It should be noted that some vehicle manufacturers install a single low-pressure switch located on the supply reservoir rather than one on each service reservoir. Although drain devices remove accumulated contaminants from the reservoirs, the air system remains 100% saturated with water vapor, which will condense when the temperature falls. To solve this problem, a desiccant air dryer, like this Bendix AD9, is installed to remove 100% of the liquid and solid contaminants and approximately 95% of the water vapor prior to entering the brake system. Before we take a closer look at the air dryer's role, let's examine its main components. The air dryer includes the supply port, end cover sump, oil separator, desiccant cartridge, desiccant drying bed, check valves, outer shell, delivery port, control port, purge valve piston, purge valve, turbo cutoff valve, and exhaust port. The air dryer is installed in the discharge line between the compressor and the supply reservoir, and also interacts with the governor. Air and contaminants from the compressor enter the air dryer supply port in the end cover. Air traveling through the end cover cools, causing some contaminants to condense and drop to the sump of the end cover. Upon exiting the end cover, air enters the oil separator, where the remaining solid and liquid contaminants are removed. Still saturated with 100% water vapor, air flows from the oil separator to the desiccant cartridge. Air flowing through the desiccant drying bed becomes progressively drier as the water vapor adheres to the desiccant material in a process known as adsorption. While some air will flow through the orifice adjacent to the check valve, the majority of the dry air exits the desiccant cartridge through its integral check valve to fill the purge volume between the desiccant cartridge and outer shell. Dry air in the purge volume flows toward the end cover and passes through the single check valve, out the delivery port, and to the supply reservoir. The air dryer will remain in the charge cycle until air brake system pressure reaches the governor cutout setting of 120 psi. The same signal of air from the governor which causes the compressor to unload also starts the air dryer purge cycle. Air from the governor enters the control port of the air dryer, moving the purge valve piston. The turbo cutoff seals the inlet port and opens the purge valve. Contaminants in the end cover sump are expelled from the open purge valve. To protect the supply reservoir against air loss, the check valve closes. At the same time, air in the purge volume and air passing through the desiccant cartridge reverse direction as the purge valve is opened. Air from the purge volume passes through the orifice adjacent to the check valve and expands to near 0 psi, becoming super dry before flowing into the desiccant cartridge. This super dry air regenerates the desiccant material by stripping away accumulated water vapor. Contaminants in the oil separator are also carried away through the open purge valve. Closing the dryer inlet port during the purge cycle ensures that loss of engine turbocharger pressure is minimized in the event the compressor intake is connected to the turbo. The entire purge cycle is complete in about 25 seconds. The purge valve will remain open until air brake system pressure is reduced to the governor cut-in setting of 100 psi. When the governor exhausts air from the compressor unloaders, air is also removed from the air dryer purge piston. With control pressure removed, the piston moves in response to its spring and closes the purge valve. The charge cycle repeats. Since the air dryer is controlled by the governor, which in turn reacts to supply reservoir pressure, it is important that air leakage in the supply reservoir be minimized for proper air dryer operation. Leakage in the supply reservoir will result in the compressor cycling between loaded and unloaded, causing the air dryer to alternate between the charge and purge cycle. It must be remembered that air loss in the supply reservoir only will not be registered on the dash gauges because of the single check valves that protect the service reservoirs. With the addition of the air dryer, the air supply system is complete. But before we close, let's quickly review what we've discussed during this presentation. The air compressor is the heart of the system. Driven by the engine, it produces and transmits compressed air to the supply reservoir. The governor connected to the compressor, air dryer, and supply reservoir maintains system pressure between a preset minimum and maximum by controlling the compression cycles of the compressor. From the supply reservoir, air flows into the service reservoirs, which are separated and protected by single check valves. Each reservoir in the system is equipped with a drain cock to drain away accumulated contaminants. With an air dryer installed, contaminants are eliminated before they can enter the system. Finally, low-pressure indicator switches and dash gauges keep the operator appraised of available brake system pressure. We hope this detailed look at your air supply system and its components has enhanced your understanding of the air brake system. Part 2 will discuss the operation and maintenance of the service brake system. This is the second of 4 programs describing the operation and maintenance of an air brake system. We'll study this system and its components. But first, let's review the devices in Program 1, the air supply system. The compressor produces compressed air for the system. Air dryers prevent contaminants from entering the system. Proper system pressure is maintained by a governor connected to the compressor, air dryer, and supply reservoir. In the supply reservoir, a safety valve protects against overpressurization. 2 service reservoirs are protected by single check valves. And last, a low-pressure indicator switch and dash gauges track pressures. Now our service brake system discussion begins at the 2 service reservoirs. They form the basis or origination point for a dual or split service brake system. To take advantage of the separate reservoirs, a dual brake valve is needed. The dual brake, actually 2 separate valves in a single housing, is operated by a single treadle or pedal. Generally, all dual brake valves function the same way. Mounting methods may differ. This is the floor-mounted E6, and this, the firewall-mounted E7. We'll use the E6 to look at the major components of a dual brake valve. The actuation components of the E6, pedal or treadle, plunger, roller, stop button, boot, and fulcrum pin are interchangeable with other brake valves. The internal components are spring seat, graduating spring, primary piston, primary inlet and exhaust valves, secondary or relay piston, and secondary inlet and exhaust valves. Air from each reservoir enters its respective supply port on the brake valve. Because the circuits are normally closed, air does not pass through the valve until a brake application. The delivery ports are open to the exhaust at atmospheric pressure, shown in yellow. With a brake application, the treadle is depressed, and the plunger applies a force on the spring seat. This compresses the graduating spring, and in turn causes the primary piston to move. The primary piston, which incorporates the exhaust valve seat, closes the primary exhaust valve. As the exhaust valve closes, the primary inlet valve is moved off its seat, and air from the primary service reservoir flows out the primary delivery port. Air from the primary delivery passes through the bleed passage and enters the relay piston cavity. Primary delivery air pressure moves the relay piston, which incorporates the exhaust seat, and closes the secondary exhaust valve. After the secondary exhaust valve closes, the secondary inlet valve is moved off its seat, and secondary reservoir air flows out its delivery port. A balanced position in the primary circuit is achieved when the primary air pressure beneath the piston exerts a force equal to that of the driver's foot on the brake treadle. The primary piston moves slightly, closing the inlet, preventing further air delivery. In this position, the secondary circuit reaches a balanced position. Air pressure on the primary and secondary sides of the relay piston equalizes. As this balance is attained, the relay piston moves, closing the inlet and preventing further air delivery. When the treadle is fully depressed, as in a panic stop, both circuits are held open mechanically and full reservoir pressure is delivered. When the brake treadle is released, the mechanical force is removed from the spring seat, graduating spring, and primary piston. Air pressure and spring load move the primary piston. The exhaust opens, and air pressure in the primary circuit goes out the exhaust port. As the air is exhausted from the primary side of the relay piston, air pressure and spring load move the relay piston, opening the secondary exhaust. If air pressure is lost in either circuit, the portion of the brake valve that still has air pressure supplied to it will continue to function. However, should air pressure be lost in the primary system, the relay piston will move by mechanical force from the driver's foot, not from air pressure delivery from the primary circuit. Here's a service tip. When only one circuit of the brake is supplied with air, the brake valve still functions. Remember this when troubleshooting for a no brakes or insufficient brakes complaint. Now let's see where the air from the brake valve goes. Vehicle manufacturers decide how the brake circuits are divided. The most commonly used is this front-rear axle split. The front axle service system is shown in orange, the rear axle system in green. The primary circuit air pressure controls the service portion of the drive or rear axle spring brakes. The secondary circuit air pressure is delivered to the steering or front axle brake chambers. The chambers located at the wheels they serve convert compressed air energy into a mechanical force. This is the front axle brake chamber. In principle, it functions like a piston in a cylinder. The brake chamber has a pressure plate and a non-pressure plate with a rubber diaphragm between them. A channel-shaped clamp ring holds them together. The return spring in the chamber holds the push plate and rod assembly against the non-pressure side of the diaphragm. There are many sizes of brake chambers. Each develops a different mechanical force. A service brake chamber's size and relative power output is specified by a number representing the square inch area of its diaphragm. This chamber is a Type 20. Its diaphragm has a 20 square inch area for air pressure to act on. With a brake application, air pressure enters the inlet port and acts upon the diaphragm. The diaphragm balloons and forces the push rod and push plate out of the chamber against the minimal resistance of the return spring. The brakes are thus applied. The force exerted against the push rod, and therefore the power of the brake application, is dependent upon the air pressure applied to the chamber diaphragm. If, for example, the brake delivered 30 psi pressure to a Type 20 chamber, the push rod would move out with a force of 600 pounds. That's 30 psi on each of the diaphragm's 20 square inches, or 20 times 30. When the brake application is released, air in the brake chamber goes out the inlet port it entered. As air pressure is removed, the return spring retracts the push rod and releases the brakes. The standard service brake chamber just reviewed is used on the steering axle. Most vehicles are equipped with spring brake actuators on the rear or drive axles. The spring brake acts as an emergency and parking brake in addition to performing the service brake function on the rear axle. The operation of the parking and emergency brake function are discussed in another part of this series. For our purposes here, let's consider the spring brake as being the same as a standard brake chamber. The components in the service side of the spring brake look the same as those in a standard brake chamber, and they serve the same function during a service brake application. Threaded on the end of the push rod is a yoke assembly for attaching the slack adjuster. The slack adjuster is the final link between the air system and the cam brake in the wheel. It multiplies and transforms the linear force developed by the brake chamber into a rotational force, or torque, used to apply the foundation brake. Slack adjusters have designations indicating the torque they are expected to tolerate. A Type 20, for example, can withstand 20,000 inch-pounds of torque. The slack adjuster also provides a means for adjusting for brake lining wear. Manual slack adjusters are currently the most popular, but they require periodic manual brake adjustment. So automatic slack adjusters like this Bendix ASA 5 Sure Stroke are available as standard on some vehicles, as an option on most. The automatic adjustment provided by the ASA 5 yields consistent brake lining to drum clearance and brake actuator stroke. Brake performance is improved, maintenance reduced. When the brakes are applied, the brake actuator's push rod causes the slack adjuster to rotate the brake camshaft, which begins to force the brake shoes into contact with the drum. As the slack adjuster rotates, the yoke assembly pivots on the yoke pin, causing the adjusting link to be pulled upward. The travel of the adjusting link actuates the internal adjusting mechanism. This adjusts the brakes before the shoes contact the drum. All adjustment ceases when the shoes contact the drum. That's important. The ASA 5 senses or adjusts to a running shoe-to-drum clearance, not a brake chamber stroke. Over and under adjustments are therefore less likely. When the brake application is released, the actuator push rod returns to the released position. The camshaft rotates in the opposite direction to its new adjusted position, and the brakes are released. Here's another service tip. Lubricate the ASA 5 every 3 months or 25,000 miles, whichever comes first, and check proper operation every time you lube it. Make a service brake application and note the length of the brake actuator push rod stroke. If too long, there could be a problem with the ASA 5 or the foundation brake itself. The system discussed so far will stop the vehicle, but additional equipment will improve performance and safety. When the brakes are released, the air pressure from the pressure side of the chamber goes back through the exhaust port of the brake valve. As airline lengths increase, air travel time to and from the brake chamber increases. Worse still, as air pressure decreases, air travel time increases, as would be the case during a brake release. Timely release of the brakes is as important as the brake application itself. So a quick release valve is installed between the chamber and the brake to shorten the brake release time. A quick release valve, such as the QR1, has only one moving part, a diaphragm. Air from the brake valve enters the QR1 at the supply port during a brake application. Entering air causes the diaphragm to seal the exhaust port. It also bends the outer edge of the diaphragm away from the valve body, allowing air to flow to the chambers being served. When the brake valve enters the holding or balanced position, air pressure above and below the QR1 diaphragm is equal. The outer edge of the diaphragm will seal against the body. The exhaust port remains sealed. Like the brake valve, the QR1 is also now in the holding or balanced position. When the brake valve application is released, the air pressure above the diaphragm is released back through the brake valve exhaust port. Air pressure beneath the diaphragm lifts it, opening the exhaust of the quick release valve. This allows air in the chambers to exhaust at the QR1 rather than traveling back to the brake valve. The QR1, most often used on the front or steering axle brakes, speeds up their release. Because the driver and the brake valve are relatively close to the front brakes, the time to supply those brakes is very short. But the brakes farther away require help from a relay valve. Use of this valve on rear axle brakes, particularly on long wheelbase vehicles, assures simultaneous application of the front and rear brakes. A relay valve is usually installed on or near the axle or axles it serves, in this case, the rear axle. The valve requires a control or service connection to the delivery of the brake valve, a supply connection to the air reservoir, and delivery connections to the brake actuators. A relay valve speeds up the application and release of the brakes. It's essentially a remote-mounted, air-controlled brake valve. It applies or releases the brakes it is connected to in response to the control air from the foot valve. A typical and one of the most popular relay valves is the R12. It consists of a relay piston with an integral exhaust seat, the inlet and exhaust valve assembly, and various O-rings. With brake application, air pressure from the primary circuit of the foot valve travels to the relay valve control port, enters the small cavity above the piston, and causes the piston to move. As the piston moves, its exhaust seat contacts the exhaust portion of the inlet exhaust valve, sealing the previously open exhaust port. Continued movement of the piston unseats the inlet valve. This allows the supply air to flow from the reservoir past the open inlet valve and into the service portion of the spring brake actuator. When air pressure beneath the piston equals the service air pressure above the piston lifts slightly and the inlet valve spring returns the inlet valve to its seat. The exhaust remains closed. The relay valve is now in the holding or balanced position, and service line pressure is equal to the delivery pressure. The brake valve is also in the holding or balanced position. If air pressure above the piston is increased, as from a stronger brake application, the piston will again move in response to the added pressure, unseating the inlet valve. The inlet valve remains open until pressure beneath the piston equals pressure above the piston. Then the inlet closes and the R12 is returned to the balanced position. When the driver removes his foot from the brake, air above the relay piston returns to the foot valve and is exhausted to atmosphere. As air pressure above the relay piston decreases, the higher pressure beneath causes the piston to move away from the exhaust valve. This allows service brake air to return to the relay valve and flow out the open exhaust port. The brakes are now released. Here's service tip number 3. Always replace a relay valve with the same or similar valve. Most service relay valves, including the R12, incorporate a differential or crack pressure. It's the amount of control air pressure needed to open the inlet valve of the relay valve assembly. The crack pressure must stay within plus or minus 1 psi. The standard R12 has a 4 psi nominal crack pressure. That is, there will be about 4 psi above the relay piston at the instant the inlet valve opens. The R12 is available with crack pressures from the standard 4 psi up to 10 psi. Brake application timing can be affected with an incorrect relay valve. Now let's look at the last device needed in our basic service brake system, the stoplight switch, an air-operated on-off electrical switch. Generally, a switch is used in each of the service circuits. 2 are used in case of a failure in either brake circuit. The Bendix SL5 stoplight switch is comprised of a body, a non-removable, non-metallic cover, piston, diaphragm, 2 contact strips with attached terminals, and a shorting bar. During a brake application, air flowing to the brake actuators or relay valve also reaches the stoplight switch inlet. Air pressure is immediately present beneath the SL5's diaphragm. When application pressure reaches or exceeds 6 psi, the diaphragm moves, carrying the piston into contact with the shorting bar. With continued movement, the shorting bar snaps into contact with the terminals, completing the circuit and lighting the stoplights. Upon release of the brakes, air is exhausted from beneath the SL5 diaphragm, the shorting bar loses contact with the terminals, and the electrical circuit is broken. That completes the basic service brake system that will safely stop a vehicle in normal service. Let's take a moment to review. The E6 receives air pressure from the system's 2 circuits and applies or releases either the front or rear brakes, regardless of failure in either. The slack adjuster rotates the brake camshaft, causing the brake shoes to contact the drums. Drum-to-lining clearance is also adjusted. Quick release valves ensure timely releases of the front or steering axle brakes. The R12 relay valve speeds up the actions of the rear brakes so the front and rear brakes apply simultaneously. Stoplights are lighted by the SL5 electrical components activated by air pressure. We hope your understanding of a simple service brake system and its components has been enhanced. This is the 3rd of 4 training programs presenting the operation and maintenance of an air brake system. We will study the emergency and parking brake system components shown. But first, let's review Program 2, the service brake system. The E6 is 2 separate brake valves in a single housing operated by a single treadle. It receives air from 2 separate reservoirs in the system's primary and secondary circuits. The E6 treats the circuits independently and applies or releases either the front or rear brakes, regardless of failure in either. Fastened to the push rod of the service brake actuators, the slack adjuster multiplies and converts linear force into a rotational force, or torque. This force rotates the brake camshaft, causing the brake shoes to contact the drum. With the ASA5 automatic slack adjuster, the drum-to-lining clearance is also adjusted upon brake application. To ensure timely release of the front or steering axle brakes, a quick release valve was added between the brake chamber and brake valve. The R12 relay valve speeds up the application and release of the rear brakes, ensuring that the front and rear brakes apply simultaneously. Brake application air that flows to the brake actuators or relay valve also enters the SL5 stoplight switch. There, an electrical circuit is completed, lighting the stoplights. Let's go on now to the emergency and parking system components, starting with double check valves, such as the Bendix DC4. A double check valve performs 2 operations. It directs airflow for specific functions, and it selects the higher pressure from either of 2 sources. Parking brakes, for instance, can be controlled from either the front or rear service reservoirs. The most common double check valve uses a shuttle contained in a guide which is installed in the body. The DC4 has 2 inlet ports and 1 delivery port. As air enters either inlet port, the moving shuttle responds to the pressure. It seals the port receiving the lower air pressure level. but the airflow continues out the delivery port. If the pressure levels reverse, the position of the shuttle will reverse. The shuttle never impedes the flow of air. Here's a service tip. With certain double-check valves used where pressure differentials may be minimal, mount them horizontally for optimum performance. The next component to be considered in the brake system is a dash control valve. The driver has several dashboard controls available. PP, or push-pull valves, are manually operable on-off air control valves. Pushing the button in places it in the delivery position. Most are pressure sensitive, like this Bendix PP1. It consists of a control button, plunger, spring, inlet exhaust valve, and body. The body has three types of ports: supply, delivery, and exhaust. The PP1 is manually applied. If supplied pressure decreases to a specified minimum setting, usually 40 psi, the PP1 will automatically move to the exhaust position. The plunger pops out, releasing air through the exhaust port. Of course, pushing the plunger back into the applied position reactivates the control. But supply air pressure must be above 40 psi for it to stay in. The PP1 is available in a range of auto exhaust settings from 20 psi through 60 psi. In part 2 of this series, we covered the rear axle spring brakes. We learned that they function as the service, parking, and emergency brakes. Let's review briefly. The service chamber has a pressure plate and a non-pressure plate with a rubber diaphragm between them. The return spring in the chamber holds the push plate and rod assembly against the non-pressure side of the diaphragm. With a brake application, air pressure enters, ballooning the diaphragm and forcing the push rod and push plate out of the chamber. The return spring's resistance is overcome, and the brakes are thus applied. The spring brake acts as the service brake on the rear axle and performs the additional function of emergency and parking brake. The rear portion, sometimes called the piggyback, has a powerful spring, diaphragm, emergency piston, emergency air inlet port, and release bolt. During vehicle startup, air pressure is applied to the diaphragm. The spring compresses, and the brakes are held in the released position until the vehicle is parked or a system failure occurs. The two sections of the spring brake utilize air pressure in an opposite manner. Air into the spring brake section releases the brakes. Air taken away applies them. Here's another service tip. The spring brake release bolt mechanically cages the parking brake spring when air pressure is not available, so you can dismantle the brake or tow a vehicle. To ensure that the spring brake portion of the spring brakes respond quickly, a relay valve is mounted at the rear of the vehicle, near the brakes it serves. The relay valve speeds the application and release of the spring brakes. A spring brake relay valve delivers or releases air to the spring brakes in response to control air received from the PP1 push-pull valve or other source. A different relay valve controls the service brakes. The Bendix R14 relay valve is essentially the R12 discussed in Part 2 of this series. The lower half of both valves are interchangeable. The R14 has an additional anti-compounding feature built in. The components for the anti-compounding feature are contained in the cover. and consist of a diaphragm and balance port. Anti-compounding, simply defined, means the avoidance of double braking. It prevents the simultaneous application of service brakes and emergency or parking brakes. The compounding of spring force and air pressure creates too much force that could possibly damage brake components. The R14 prevents this from occurring. To accomplish this, a line is connected from the delivery side of the service relay valve to the balance port of the R14. With no air pressure at the service port of the R14, the parking brakes are applied. If a service brake application is made, air from the R12 relay valve enters the balance port of the R14's quick release. The diaphragm moves, blocking the service port. Air from the balance port flows into the cavity above the relay piston, forces the piston down, opening the inlet, delivering air to the spring brake cavity. The R14, through its anti-compounding feature, assures that the parking brakes are released with the same amount of air pressure as the R12 is delivering to the service brake. The next component in the system is the optional SR1 spring brake valve. It's most often used on longer wheelbase vehicles, but can be used on tractors and straight trucks. Its primary function is to maintain modulated rear axle braking if primary reservoir air pressure is lost. Modulation takes place through the service foot brake, taking advantage of a driver's natural reactions in an emergency. In a rear axle brake system failure, the SR1 modulates the pressure delivered to the rear axle spring brakes in direct proportion to the amount of pressure delivered to the front axle brakes. The SR1 has 4 ports: the number 1 reservoir port connected to the rear axle reservoir, the control port connected to the front axle delivery circuit of the dual foot valve, a supply port to the delivery of the PP1, and a delivery port to the control of the R14 relay valve supplying air to the spring brake cavities. Inside, the SR1 contains 2 pistons. We'll call them piston A and B. Below each piston is an inlet exhaust valve, and above are the springs. The final component is a single check valve. As soon as air pressure starts to build in the rear axle service reservoir, it is also present at the underside of piston A, which is held all the way down with spring force. Its exhaust is sealed, and its inlet is open. As air pressure in the primary reservoir reaches 55 psi, enough pressure is also under piston A to move it up against the spring force. When the piston moves up, the inlet valve seats itself. Continued movement upward unseats the exhaust. As the system continues to charge up to 120 psi, the driver may elect to release the spring brakes. Pushing in the PP1 control valve delivers air from the PP1 to the supply port of the SR1. Piston B, held down by spring force, seals off the exhaust and holds the inlet open. Air pressure from the PP1 enters the supply port, flows past the open inlet valve under piston B, and onto the spring brakes. When the air pressure going to the spring brakes beneath piston B is about 95 psi, piston B rises slightly, closing the inlet, but not enough to open the exhaust. A balanced state is achieved. Both the exhaust and the inlet are closed. The spring brakes are released. The vehicle can be moved. A normal service brake application at this point has no effect on the SR1. Air flows to the front axle service brakes and to the control port of the SR1. It stops there because the inlet valve under piston A is closed. The rear axle brakes also apply normally using air pressure from the foot valve. The SR1 will not be affected by a front axle service brake failure. It monitors only rear axle service brake reservoir pressure. The spring brake will remain released because of the double check valve. The rear axle service reservoir will continue to supply air to the PP1, and the PP1 will continue to supply the SR1. If rear axle air pressure is lost, the driver will be warned, and the shuttle in the double check valve will move to allow the front axle reservoir to supply the R14 relay valve and the PP1. Even though air pressure for the spring brakes is shown in yellow, the orange front axle service reservoir is supplying the air pressure. However, as pressure drops in the rear axle reservoir, air pressure at the number 1 reservoir port of the SR1 drops, causing piston A to move down due to spring force, sealing the open exhaust passage, and with continued movement to unseat the inlet valve. When the driver receives a low-pressure warning and applies the brakes, only the front axle service pressure will be available. The front axle brakes apply normally, and the same air pressure is delivered to the control port of the SR1. The front axle application air will enter the control port, flow by the open inlet valve, and through the internal passage to the outer surface of piston B. The pressure there will cause piston B to rise, opening the exhaust valve. Air pressure in the spring brakes will be exhausted until the springs are allowed to achieve a balance, reducing the pressure under the inner diameter of piston B. As a specific example, if a 20 psi pressure application is made to the front axle brakes, 20 psi is delivered to the control port of the SR1. It represents a 20 psi control pressure and exhausts enough pressure from the spring brakes to simulate mechanically a 20 psi air application to the service side of the spring brakes. When the foot brake is released, the air pressure in the outer area of piston B is exhausted back through the foot valve. The springs above piston B move it down, opening the inlet, allowing air from the front service reservoir to flow through the double check valve, the PP1, the open inlet of the SR1, and into the spring brakes to recharge them. The spring brakes can be applied and released or modulated on and off about 5 times. Here's a service tip. The number of brake applications depends primarily on the severity of brake application, reservoir size, and degree of reservoir contamination. One reason to drain reservoirs regularly is that the volume of contamination reduces the volume of air available. The SR1's internal check valve assists the exhaust action from the spring brake. Piston B is in the balanced position when the spring brakes are released. The inlet exhaust valve beneath piston B is closed. The check valve is closed because of the spring force and the fact that the pressure beneath the check valve is slightly greater than the pressure above it. When the PP1 park control is put in the park position, air from beneath the inlet valve returns to the open exhaust of the PP1. The pressure above the check valve becomes greater than that below it. The check valve opens. This allows the spring brake hold-off pressure to also flow back to the open exhaust of the dash control. Pressure beneath piston B is then reduced. The springs above piston B can move the piston down, opening the inlet valve. This enlarges the path for air to return to the PP1 exhaust. When the air is completely exhausted, the vehicle parking brakes are fully applied. That concludes our presentation of the parking and emergency brake system. Let's review the devices briefly. The DC-4 double check valve directs airflow to the PP1 from either of two reservoirs, whichever has the higher pressure. The manually operated push-pull PP1 moves from the applied to the exhaust position automatically when supply pressure reaches a designated minimum. Spring brakes and chambers convert air pressure energy to mechanical force to apply the brakes. Relay valves speed up the application and releases of brakes, particularly the rear axle brakes. In dual brake systems, the SR1 spring brake valve supplies a limited hold-off pressure to the spring brakes and causes a mechanical application of the rear brakes if there is a loss of rear axle service pressure. The first three parts of this series have covered a complete air brake system used on a typical straight truck or bus. Part 4 will present the additional components unique to an air brake tractor and the components necessary in a trailer system. We hope we have increased your understanding of the parking and emergency brake system and its components. In the first three parts of this presentation, a complete air brake system for a straight truck or bus was explained. In this, the fourth and final presentation, we'll add the components to a straight truck which are necessary to tow an air brake trailer. Then we'll look at the trailer air brake system itself. Let's begin. In order to tow a trailer, a truck must be able to charge it with air and transmit brake signals to it. Two air hoses extend between the tractor and the trailer to fulfill this function. They are called the trailer supply and trailer service lines. The opening and closing of these two lines during normal and emergency operation is controlled by the tractor protection system, which is composed of two valves. There are a number of different valves that can be used. In this program, we'll look at the most basic and popular, the TP3 tractor protection valve, and a control called the PP7 trailer supply valve. Mounted at the rear of the cab, the TP3 tractor protection valve functions as an on-off control for the service line, which carries brake applications from the tractor to the trailer. The TP3 is a simple valve internally and consists of a body, the plunger with its integral service valve, and a spring. There are four air connections on the TP3, the tractor supply and tractor service ports on one side, and trailer supply and trailer service ports on the opposite side of the body. Each is identified with cast-in lettering. Air exerts a force on the plunger as it flows through the TP3 from the tractor supply to the trailer supply port on its way to the trailer air system. When air pressure on the plunger exceeds approximately 45 psi, the plunger moves, opening the service inlet valve. With the service valve open, brake application pressure is free to flow from the tractor to the trailer brake system. The other half of the team, the PP7 trailer supply valve, is mounted on the vehicle dash and is easily distinguished by its red octagonal control button. The PP7 controls the flow of supply air to the TP3 and subsequently to the trailer. In addition, it synchronizes the tractor protection system with the tractor parking system. One-button parking control is thus achieved. Like the PP1, the PP7 button must be pushed in manually, but will pop out and exhaust automatically if the air supply drops below approximately 40 psi. Supply pressure of 50 psi or greater assures that the button will remain in until manually pulled or supply pressure drops below 40 psi. The PP7 is a combination of two pressure-sensitive on-off control valves in one body. The upper portion is almost identical to the PP1 push-pull control we studied in Part 3 of this series, while the lower half contains an SV1 synchro valve. The upper half of the PP7 consists of a control button, plunger, spring, and inlet exhaust valve. The lower half contains a piston, piston return spring, inlet exhaust valve, and valve spring. In addition to an exhaust vent and exhaust port, the PP7 body has three air connections: supply port, delivery port, and control port. The supply port is connected to the same double check valve that supplies the PP1 park control. It is therefore assured a constant supply of air pressure regardless of a failure in one of the service reservoirs. The delivery of the PP7 is connected to the tractor supply port of the TP3, and the control port is connected to the delivery of the PP1 trailer release valve. With the vehicle parked and no air pressure in the system, the PP7 control button is out. The inlets of both valves inside the PP7 are closed, and the exhausts are open. When tractor system pressure builds to 50 psi or greater, the PP7 can be depressed and will remain in. With the plunger inlet open and the exhaust closed, air flows from the supply port to the closed synchro valve inlet. The synchro valve piston remains down due to a lack of air pressure at the control port. The PP7 delivery port remains open to exhaust. When the PP1 park control is depressed, air pressure simultaneously releases the tractor spring brakes and is delivered to the PP7 control port. Air pressure at the PP7 control port moves the synchro valve piston, sealing its exhaust passage and opening the inlet valve. Air from the push-pull section of the PP7 flows past the open synchro valve inlet and out the delivery port, then through the TP3 to charge the trailer reservoirs. If tractor air system pressure falls to approximately 40 psi during vehicle operation, the PP7 button will pop out. Air from the trailer's supply line is exhausted at the PP7. This preserves the last 40 psi of tractor air pressure and causes the trailer parking brakes to apply. Note that the synchro piston remains unaffected. If the PP7 button is held in and tractor air pressure has dropped to approximately 20 psi, the synchro piston automatically moves into the exhaust position. Although the driver continues to hold the button down, the trailer's supply line is exhausted and trailer parking brakes are fully applied. During a trailer breakaway or a sudden complete trailer supply line failure, the PP7 button will pop out automatically. The tractor air system will retain between 40 psi and full system pressure depending upon the location and severity of the failure. Air escaping from the failed supply line cannot be replaced through the PP7 supply port as fast as it's lost. This causes pressure inside the PP7 to drop below the 40 psi pop-out pressure, even though supply port pressure is much higher. Because of the synchro valve section in the PP7, the tractor protection system is linked to the tractor parking brakes. To park a tractor-trailer combination, the PP1 park control is pulled out. Air is exhausted from the tractor spring brakes and from the PP7 control port. With no air pressure at the PP7 control port, the synchro valve piston moves, seating the inlet valve and opening the exhaust passage between the PP7 delivery and exhaust ports. Air from the trailer supply line returns to the PP7 and is exhausted, causing the trailer parking brakes to apply. Note that the PP7 button remains in. This is due to the PP7 synchro valve exhausting the trailer supply line. Pushing the PP1 park control in releases the tractor parking brakes and delivers air to the PP7 control port. This causes the synchro valve piston to close its exhaust and open the inlet. The trailer supply line is recharged and the trailer parking brakes release. To disconnect the tractor and trailer, the operator must pull the PP7 button. Pulling the button closes the plunger inlet and unseats the exhaust valve. Air that was flowing out the delivery port returns to the PP7 and exhausts from its vent. Test the tractor protection system by pulling the PP7 out and making and holding a brake application. Apply a soap solution to the trailer service and supply line hose couplings to see if the TP3 or PP7 is leaking. Our basic tractor system is almost complete, but before moving on, we must consider one additional device, the DS2 double check valve and stoplight switch. We learned in Part 2 that vehicles are equipped with dual brake systems, a protected braking circuit for the front axle brakes and a separate circuit for the rear. Since there is only one service line leading to the trailer, one or the other of the two braking circuits must be chosen to apply the trailer brakes. And, of course, the stop lights must be lighted regardless of which is chosen. That's the function of the DS2. It's a combination of two valves, the SL5 stoplight switch from Part 2 and the double check valve from Part 3. Like a standard double check valve, the DS2 has two inlet ports and one outlet port. The stoplight switch is positioned in the middle of the double check valve opposite the single outlet port. A shuttle riding in a guide travels between the two inlets. Lines from the front and rear axle brake circuits connect to the inlet ports on opposite sides of the DS2. The outlet is normally mounted to the tractor service port of the TP3 tractor protection valve. During normal operation, brake application air from both brake circuits enters the DS2 inlet ports. Since the rear axle brake circuit pressure is slightly higher, the shuttle will move to close the front circuit side, at the same time moving the stoplight piston to light the brake lights. Rear axle application air flows to the outlet port, then through the TP3 and on to apply the trailer brakes. If one brake circuit on the tractor loses air pressure, brake applications from the remaining circuit would still flow through the DS2 to apply the trailer brakes and light the stoplights. Before going on to the trailer brake system, there is one accessory that should be considered: the BP R1 bobtail proportioning relay valve. The BP R1 combines a relay valve with a proportioning valve. It was designed for use in tractor brake systems only and replaces the standard R12 service relay presented in Part 2. The BP R1 improves control and reduces stopping distances by proportioning brake applications to the lighter rear axle brakes during bobtail tractor operation. The BP R1 body contains a standard service brake relay valve, while the cover houses the proportioning valve. There are 4 delivery ports, 2 supply ports, one control port for the relay valve, and another for the proportioning valve. All air connections are identified with cast-in letters. With the exception of the additional proportioning valve control port, the BP-R1 air connections are exactly the same as the R12 relay it replaces. This port is connected to the air line running between the PP7 trailer supply valve and TP3 tractor protection valve. During tractor-trailer operation, the PP7 delivers air pressure to the trailer and to the control port of the BP-R1. So long as control port air pressure is present, the BP-R1 functions as a standard service relay valve and delivers full braking pressure to the tractor's rear service chambers. When the PP7 trailer supply valve is pulled, the trailer supply line is exhausted. Pressure is removed from the BP-R1 control port, signaling that the tractor is now in bobtail operation. With the weight of the trailer removed, the tractor rear brakes are overpowered. In bobtail operation, the front brakes are capable of doing more to stop the vehicle than the rear brakes. They can use a much higher application pressure than the rear brakes. When the driver makes an application strong enough to take advantage of the stopping power of the front brakes, the rears skid and vehicle stability is diminished. The BP-R1 compensates for this by reducing application pressure to the rear brakes only and permits the driver to apply the foot valve in a normal manner. This takes full advantage of the front brakes without locking the rears. Vehicle stopping distances and stability are improved. Here's an important tip. Only vented dummy hose couplings can be used with the BP-R1, and the vent must be open. With the addition of the BP-R1, the basic tractor system is complete. Let's now turn our attention to the trailer and look at a schematic of the entire system. The two lines that carry air into the trailer supply and trailer service lines, are connected to their corresponding air lines from the tractor. A hose coupling, or glad hands, installed at the front or nose of the trailer, connect these lines. The trailer reservoirs serve the same function as they do on the tractor. Two reservoirs are used because this trailer has two axles, and Safety Standard 121 requires a minimum reservoir volume for trailer service brakes. An R12 relay valve, identical in operation and function to the one described in Part 2, is attached to one of the two reservoirs. Its delivery lines are connected to the service side of 4 spring brakes, identical to those described in Part 3. The trailer service line connects to the control port of the R12 and carries brake signals from the tractor service brake system to the R12. The R12 assures the trailer service brakes apply in unison with the tractor service brakes. The trailer service line also connects to the SR5, the last valve to be considered on the trailer brake system. The SR5 protects trailer air pressure and automatically applies trailer spring brakes in the event of a breakaway or trailer supply line failure. In addition, it permits intentional and repeated spring brake applications and releases. But it also prevents automatic applications when trailer reservoir air is lost. An optional anti-compounding feature prevents simultaneous application of service and parking brakes. Like many of the valves we've presented, the SR5 incorporates several individual components in a single housing. A relay valve lies at the heart of the SR5 and is comprised of a control piston and inlet exhaust valve. Along with the relay, there are 4 single check valves, B, D, E, F, and pressure protection valve, C. A male stud is used to mount the SR5 to the reservoir. A line from the SR5 service reservoir port connects to the same reservoir. The trailer supply and service lines connect to SR5 ports with the same name. SR5 delivery ports connect to the emergency side of the spring brakes. Let's take a look at how the SR5 operates, beginning with no air pressure in the trailer. Air flows through the trailer supply line, enters the SR5 trailer supply port, and encounters the relay piston. The relay piston moves into contact with the inlet exhaust valve, sealing the piston exhaust passage. Piston travel continues and opens the inlet. At the same time, air flows through passage A, then check valve B, past the open inlet, and into the spring brake cavities, releasing the spring brakes. Concurrently, air pressure acts on pressure protection valve C. At approximately 85 psi, valve C opens, allowing air to flow past check valve D to charge the trailer reservoirs. The trailer brake system is now ready for operation. If air in the trailer supply line is removed for any reason, whether to park the vehicle using tractor dash controls or due to a tractor-trailer breakaway, the spring brakes will immediately apply. Without pressure at the SR5 trailer supply port, the control piston moves, closing the inlet and opening the exhaust. Air from the spring brakes flows through the passage in the control piston and the spring brakes apply. Check valves B and D, along with pressure protection valve C, close to protect air pressure in the reservoirs. If supply line pressure was exhausted due to a park application, the trailer spring brakes are easily released by actuating the dash controls in the tractor to recharge the supply line. The trailer service line carries the brake application air from the tractor to the trailer. That air flows to the service relay valve and SR5 trailer service port. A single check valve in the SR5 cover prevents simultaneous spring and service brake applications, which creates extra load on foundation brake components. If a trailer service application is held at the same instant a park application is made, air in the service line flows through the single check valve, out the trailer supply line, and exhausts through the PP7 in the tractor. Future compounding is prevented by the closed tractor protection valve. Let's look at what occurs when trailer reservoir pressure is lost. First, trailer service braking is no longer available, since the R12 depends on reservoir pressure to apply the brakes. Inside the SR5, pressure protection valve C will close at approximately 70 psi, retaining air pressure in the trailer supply line. The air trapped in the trailer supply line by the closed pressure protection valve will continue to hold the piston's inlet valve open, supplying air to the spring brakes. Automatic spring brake application is prevented. However, trailer supply line air can be used to apply and release the trailer's spring brakes repeatedly. Before we close, let's recap. In order to pull an air brake trailer, a truck requires a tractor protection system comprised of a PP7 trailer supply valve and TP3 tractor protection valve. A DS2 double check valve and stoplight switch selects the highest pressure from the two service brake circuits on the tractor to apply the trailer brakes. In addition, it lights the stoplights regardless of which circuit is selected. The BP-R1 bobtail brake proportioning relay is an accessory that replaces the standard relay valve and provides increased brake control during bobtail tractor operation. The trailer brake system is comprised of spring brakes for service and emergency braking, an R12 relay valve like the one used on the tractor for rapid application and release of trailer service brakes, reservoirs to store compressed air for service braking, and finally, the SR5 trailer spring brake valve to control parking and emergency applications. An enormous amount of information has been covered in this series. Should you have missed any part of this four-part presentation of a tractor and trailer air brake system, we urge you to take the time to review all four parts. One final note. While much was covered, other system combinations and optional components are available, so the system presented is not necessarily exactly like your own.